All right, in this lesson, we're going to look at the difference between series and parallel circuits, and then we're going to learn to calculate what's called equivalent resistance. Let's talk about that first. Equivalent resistance is another way of saying the total resistance. So I'm going to write down RT. In a circuit, we usually have more than one resistor. When you have more than one resistor, then you have to calculate the total resistance of the circuit. And it's a little bit more complicated than just adding up the resistors. And the other thing I want to mention is that this skill of learning to calculate the equivalent resistance is the first thing that we need to be able to do as we move into our next lesson. And you will not be able to do the next lesson unless you know how to calculate equivalent resistance. So please take your time on this and make sure that you really, really understand it. Okay, here it goes. Number one, a series circuit is a circuit in which the current passes through each circuit component without branching. So the current passes through each circuit component without branching. All right, what I mean by that, it's going to be convenient for you to always picture yourself being a marching electron. So right now, if you are a marching electron, you are going to come out of the positive side of the battery. Remember conventional current. Okay, so here you go. So we're going to picture you, and I draw the marching ants or the marching electrons with dots. So here go the dots. Marching electrons go around, they go through resistor 1, they go through resistor 2, march, 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 they go through resistor 3, and then they're back at the battery. That's what we mean by without branching. We made a complete circle. If you make a complete circle, you have a series circuit. All right, but look at a parallel circuit. Is a circuit in which the current divides into two or more paths. So I'm going to write down the word current has a choice. Current has a choice. All right, so here you are. You are the marching electron coming out of the positive side of the battery. So march, 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 right there. I'm going to circle that little dot. That dot is called the junction. A junction is when you have a choice. You now could go through R1, so you could go like this, march, 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 march. And you could be back, or maybe your friend came out of the battery and went like this, march, 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 march. Oh, look, he has a choice. He's reached a junction. He could go instead through R2, march, march, march. Or you have another friend who went march, 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 march. He went straight. He went straight. And so you see we have three different paths. We have this first path right there. We have a second choice. And we had a third choice. Three ways to get around this circuit. So it doesn't matter how many choices that you have or how many ways there are to get around the circuit. Anytime there is a junction, that there's a choice, you have a parallel circuit. So that's just the only part that you need to recognize. But in real life, our circuits, if we had them built on our table, it's not as always easy to see. So let's pretend this is our lab table. We have a battery here. We have a wire connected to the start of a switch. Then they have a switch and another wire, a light bulb, wire, light bulb. Okay, so now I have to draw this circuit. And when you draw a circuit diagram, you have to make it boxy. And I try to make it as close to the replica as possible. So I see the battery over here. So I might do something like this. I'm going to make the positive side of the battery here just because I feel like it. And that would mean my electrons would be going this way. And then I'm going to put my switch in. A switch is like a door. So I just put a door. And so the door can open and close. And then I come around and I see a light bulb. A light bulb is a resistor, and I see another light bulb over here. Now, because this is a complete circle, I honestly could have put these components anywhere I wanted them on the circle. It would not have changed my circuit in any way, but I try to make my diagram look as closely as possible to mimic the actual circuit on my table. All right, this one I have, looks like a switch. Okay, but here's the battery. I see a switch. I see a light bulb. And look at this, like battery, light bulb, switch. That's like one possible way to get around this circuit. But I also see that somebody could do this. They could come out of the battery. They could, instead of going through that first light bulb, they could have gone through this. So like this blue path never went through that light bulb. So that tells me that this is going to be a parallel circuit. So I'm going to draw a parallel circuit like this. And I'm going to put a second thing here. And I'm going to put over here my battery. So here's my battery. I'm going to put my switch right here, my door. And then I'll do this first light bulb. So that would be like the first path around, going through the first light bulb. But somebody could have gone through the outside path and gone this way. I'll do it in a different color. They could have gone this way and bypassed that first light bulb. So that's going to be a parallel circuit. And the reason that you have to recognize what kind of circuit it is there are different equations for calculating the equivalent resistance. So I told you to think of the equivalent resistance as like the total resistance, but equivalent resistance is written as REQ to stand for the word equivalent. So if you have a series circuit, the equivalent resistance truly is the total resistance. So you take the resistance value of your first resistor, you add it to the resistance value of your second resistor, you add it to your third, I'll say plus dot, dot, dot. However many you have, you just add them together. So series circuits are pretty easy. Parallel circuits are a little bit more complicated. I call them, they are 1/overs. So 1 over REQ equals 1 over the first value plus 1 over the second value plus 1 over the third value, dot, 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 however many that you have. So let's practice that here really quick. So I would like you to get your calculator out and literally practice this with me. Pause the video when you're doing your number crunching because getting it out of your calculator is half of the problem here. All right, so here we have a simple series circuit, and we're going to pretend that the resistance of every resistor is 5. So I'm going to write down 5, 5, 5. Because it's a simple series circuit, I just add them up. So the REQ of this circuit is going to be 15 ohms. So I need to know that because when I go into my problem solving in the next lesson, I'm not going to use 5s, I'm going to use 15. All right, here we have a parallel circuit, and I know that because I have junctions and I have choices. I can go this way, I can go this way, I can go this way. So I'm going to, if each of these is 5, so it means that the answer, REQ, but it's 1 over, is going to be 1 over 5 plus 1 over 5 plus 1 over 5. You know what? This one we don't need our calculator, so let me keep going. 1/5 plus 1/5 plus 1/5 equals 3/5. 3/5. But that's not the answer. That's 1 over the answer, which means I'm just going to flip it over. So REQ is going to be 5 over 3. But we're going to need decimal answers. And so let me see if my calculator screen will show up here. So how I like to do it is like this. 1 divided by 5 plus 1 divided by 5 plus 1 divided by 5. And then 1 over the answer, flip it over. and I get an answer of 1.67 equals 1.67 ohms, which obviously 5 divided by 3 is 1.67, so we are in business. Okay, that's the bare minimum. Now it's when it gets a little bit more complicated. All right, so you can start to see here that we're going to have some fancy circuits. Fancy. And when you have fancy circuits, they are called combination circuits. Combination circuits means that there's some pieces of the circuit that are in series, and there's some pieces of the circuit that are in parallel, and we have to find the REQ of each of these complex circuits or combination circuits. All right, here's the hard part. And honestly, some of you are going to catch on like right away, and others of you, it takes a few days. And I say the word days. Okay, so the hard part is there are no concrete rules that I can tell you that will work 100% of the time. Instead, there has to be like some sort of intuition that you have that you kind of like figure out how to do this. But I can give you some hints. It says analyze mini circuits first and start as far away from the battery as possible, then move towards the battery. So we need to figure out what that means. All right, I got to do number 8 here first. All right, it says determine the equivalent resistance by constructing equivalent circuits on a separate sheet of paper. Do not skimp on drawing equivalent circuits or you will not be able to do the next lesson. So you're not going to like how I'm going to ask you to write all of this down, because you're going to start, when you finally catch on, you're going to just say, I can do this on my calculator. I can go number crunch, and I can be done. But then you won't be able to do the next lesson. All right, so we are going to learn in the next lesson to solve complex circuits. And when I say solve complex circuits, what I mean by that is we are going to have a circuit and we're going to have a whole bunch of questions that people ask us about the circuit. We will have no possible way of answering all those questions unless we fill in all of this space with our equivalent circuit charts. And that's what we're learning to do today. We're not learning to just get an answer. We're learning to draw all of the necessary charts that we're going to need for this next lesson. So that's the part that I'm going to demo for you here on a sheet of lined paper. So you will also need to do this on a sheet of lined paper. So let me kind of explain and model at the same time. So the first thing I have to do is I have to draw this circuit. So I see that this circuit's kind of boxy. So I'm going to draw it kind of boxy like this. And then there's this thing coming over here. So let's do that like this. All right, and I see that I have a battery. It happens to be a 30-volt battery, but I don't need the volts today, so I'm not going to write that down. I do have a resistor here. I have one here. I have one here, and I have one here. This one is 12 ohms. This one is 18. This one is 9, and this one is 6. Okay, so first of all, when I start here, you might be confused saying, well, I wouldn't have done that, but you're just trying to kind of catch on to the pattern here a little bit. All right, so when I say to you a hint, analyze mini circuits first. Mini circuits means like look for little conglomerations. This to me is a mini circuit right there. So picture this. The electrons come out of the battery. They marching around. They come down here. And when they get to this spot right here, I'll make it dark. That's a junction. They have a choice. They can choose to go up, they can choose to go straight, or they can choose to go down. That tells me that these 3 resistors are in parallel. So what I'm going to do now is this is called the original circuit. And now these are called the circuit charts. Okay, so now I'm going to, when we draw a circuit chart over here, we kind of draw it smaller, mini. All right, I'm going to draw the battery back. I'm I'm going to draw this 12. All right, but what I'm saying to you is whoever made the original circuit chose to put in an 18, a 9, and a 6 ohm resistor in parallel. We could instead go to Radio Shack, and now I'm going to write the word REQ. Instead of putting these three things in parallel, I could just put the equivalent resistance in here and not use these three. So what would this equivalent resistance be? Well, it would be 1 over REQ equals 1 over 18 plus 1 over 9 plus 1 over 6. So you could work on common denominators and all that kind of stuff, or I could just do it in my calculator. Let me switch calculators for a minute and see if this one shows up better. Yeah, I think it does. Okay, so I'm going to do 1 divided by 18. Whoops. 1 divided by 18 plus 1 divided by 9 plus 1 divided by 6. And then 1 over the answer, because I got to flip it, and it's 3. So the REQ equals 3. So instead of doing these 3 little resistors, I could have just bought a 3 ohm resistor, and then my circuit would function the same way. Now, in reality, there was probably a reason that they chose this configuration, but mathematically, it's equivalent to a 3. So now I have a 12 and a 3. And so you circle what you're replacing, and then you write down the answer, and you call it an REQ. We need to know that because in the next lesson, we need to know that this is not a real resistor. It's just an equivalent value. And what does it stand for? It always stands for, you look back at the next picture. Oh, it stands for those 3 things that I circled. That's why it's important that we have to circle them. All right, so now I have to draw another picture. When you draw more pictures, you draw your pictures down. All right, so I'm going to draw another picture. And I have a battery here. And now I look at the marching electrons. They come out of the here, they march, march, march. They go through the 3, they go through the 12, back, 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 back. And that tells me there were no choices. Like if I went through the 3, I had to go through the 12. That means this is in series. So these 2 guys are in series. So I'm going to circle them. And I could instead of using the 12 and the 3, I could go to Radio Shack and I could instead buy an REQ. Remember that if they're in series, I can just add them. So 15. If I put a 15 ohm resistor in, the circuit would function the same way. So this battery with this 15, my circuit functions the same way as this battery and all of this mess that I have going on up here. This 15 stands for whatever you circled in the previous picture. How do you know when you're done and you don't have to draw any more pictures? You are always done when you have one battery, and our battery is what? 30 volts. I'll write down 30 volts. And one REQ. One battery and one REQ. We're not going to do this today, but in the next lesson, the next thing we would do is use VEER. And that's why we need a V value and we need an REQ because that's going to go in the VEER. So we are always taking our combination circuit and drawing little mini circuits down a list until we get one battery and one resistor. And usually this work would not be here. I create this big empty space that I'm going to be putting a chart in come tomorrow. And then we'll be able to do some things in our chart and answer all the questions in the bottom. So right now, today, I'm trying to get you used to how to draw all these pictures and how to draw all these mini things, because we are actually going to do something with this picture. tomorrow. We are actually going to do something with this picture tomorrow. And if all you know is that the answer is 15, then I'm going to say to you, but where's your picture? Because we need it. Where's this picture? We need it. So we have to learn to draw the pictures today. Okay, so there's number 9, and we know that number 9 turned out to be an REQ of 15, and we learned to draw the pictures. All right, let's look at the next one. All right, so I'm going to start by drawing a picture of the circuit. And so I see kind of something that looks, I'm going to call this 9A. We're going to call this 9B. 9B. All right, I see something that looks kind of like a box like this. And then I see this coming there, this coming here, and then I'll hook them together. So I have a battery. So they kind of have a double battery, but I'm not going to draw a double battery. So 24 volts. They have a resistor here, a resistor, a resistor, and a resistor. So this is a 100. This is a 350, a 250, and a 200. Okay, this is another example of what I would call mini circuits. All right, I'm going to look for mini things, and I think you can see a mini thing right now. This is a mini thing. All right, let's tackle this one. We can only tackle one thing at a time. So I know you might want to do that one at the same time, but we can't. All right, so to figure out, are these, like some people think these are in series because it looks like a circle, and some people think they're in parallel because they're like in parallel lines. And how do you know? Pretend you are the marching electron. So here we go. March, 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 march. When I get right here, look at, I have a choice. I can get around the circle by going the 250 way and then exit, or I can get around the circle by going the 100 way and then exit. And it's not a series unless it forces you through both of them. So these guys are in parallel. So that tells me then I'm going to redraw my circuit over here a little bit smaller. And I'm going to keep this box. But I'm going to get rid of this box. I'm going to put my battery back in. Got to keep this guy. Got to keep this guy. I should label those 200 and 350. But I am going to choose to, instead of using a 100 and a 250, I'm going to replace them with this REQ. I just got to figure out, if I went to Radio Shack, what I would have to buy. So we already figured out they're in parallel. So that means I'm going to go 1 divided by 100 plus 1 divided by 250. And then I got to flip it over, 1 divided by the answer. And I get 71.43. 71.43. So if I bought a 71.43, my circuit would function in the same way. All right, the next step, I now think I'm going to combine these guys. So I got to draw another picture. I know this is tedious. I know it's a pain. But to be honest, I kind of like drawing circuit pictures. Okay, so I have my battery. We already have an REQ. By the way, I always make my REQs a different color. I don't know if you've noticed that, because it's going to be another visual when I do my work tomorrow, that these are not real resistors. These are the REQs. All right, so what are we going to replace this guy with? Let's figure out what kind of circuit it is. So picture the marching electrons. They'd come around. They get right here. Some of them can go the 200 way. Some of them can go the 350 way. So this definitely is a parallel. So we're going to do 1 divided by 350 plus 1 divided by 200. 1 divided by the answer. I get 127.27. So REQ 127.27. All right, now looks like I think I got one more picture to draw, and your pictures then start to get smaller. Okay, we're kind of like collapsing our circuit over here. So I have my battery that's 24 volts. And now I'm going to combine these guys. All right, let's talk about our marching electrons for a minute. They come out of the circuit. They go through this REQ. They're forced to go through this REQ to get back. So that tells me that these guys must be in series, which means that I can replace them with an REQ of, remember when things are in series, we can just add them. So we have that number plus 71.43. Oops, I missed the 71. 71 point, I missed it again. 71.43. 198.7. 198.7. And now I know that I'm done, because if I wanted to do VEER, this is an REQ, I would have my voltage, I would have my REQ value, and then I could calculate the I, which will be the first step tomorrow. So this turned out to be an REQ of 198.7. Okay, so I want you to have a chance to try some of these. So I'm just going to kind of give you a little hint here, a couple of hints along the way, but I want to see what you get, and you can post your REQ answers on the discussion board, and we will look for consistencies. And if you want to share your work on the discussion board, you need to take a picture of this whole page so people can see what you did. But as we move into, I'll call this part C here, there's lots of places that you could start, but you know what? I find the miniest thing to do. I think I'd start with these guys first. And those guys look like they're in series, because if you march around here, this is a choice. I can go this way or I can go this way, but whoever goes this way has to go through both of them. So I would combine those two first. In my next picture, then I think I'd combine this one and this answer. And then maybe in my next picture, I would combine these guys first. And then maybe I would do this branch and then this branch, combine those. Then I would have this answer, and I have this answer, and then I can combine those. Same thing over here. I would start the miniest thing that you see first. I think I maybe would start with this. And then maybe you'd combine this answer with this one. And then in the next picture, this one with this one. And then this branch with this branch. And then this with this. And hopefully you'll kind of start to catch on how we should do that. We really haven't gotten an example yet of starting as far away from the battery as possible. It looks like that example might show up in our notes in the next lesson. All right, I'm curious to see how you do. Please share your work and your answers on the discussion board. But to test yourself, the homework assignment that goes along with this lesson is a WebAssign that's called Equivalent Resistance. And you'll notice on the WebAssign, I think some of the questions are maybe a little bit easier than these. And but you know what? These are some hard ones. And if you can do these, we can handle any circuit that's going to be thrown at us. Okay, good luck. I'm anxious to see how you do.